the triplex or the centrifugal pump? Yeah, the triplex is going to have more maintenance on it. The triplex quintuplex, the PD pump, is going to have more maintenance on it than that centrifugal. The centrifugal will experience some wear as it goes, if it gets a lot of solids going through the impellers and through the case, but not to the extent that you see the wear on this. In both cases, we want to clean up the water as much as we can anyway, but these are high maintenance items compared to the centrifugals. This is a multi-stage centrifugal pump. First, let me say these pictures were taken with a technique called a Polaroid. Does anybody remember Polaroid pictures? Have you ever seen one?
Just me.
So this is the multi-stage centrifugal, and remember Oxy had a lot of these. They had them sitting outside. These are inside a station. Here's a multi-stage centrifugal pump. The suction comes from a tank just outside the building, straight into the pump, goes through this discharge piping, and then let's go up to this picture. It goes to this valve, which is a control valve, then on down the line, and as we come down from the line, there's a branch in it with another control valve for bypass volumes. So the flow through the pump is out of the tank, through the pump, to a control valve, which is only used on startup, and then out to the header distribution system, but also to a diverting system for bypass. And schematically, it looks like this. The head tank goes to the pump. We want to start the pump, the centrifugal pump, against a closed valve. Remember the pump curves for centrifugal pumps. If they have no head, they go to maximum volume. And they will spin at maximum volume, and this motor will just keep going until it overloads. So we started against a closed valve. And this valve will start to open as it sees pressure develop in the system. And then it will gradually open until the system pressure is felt by the pump. And then it will be leveled out and can continue to pump. This will keep this regulated though. So early on, when we first put the wells on injection, this system pressure is going to be way low, isn't it? Because of the void that we're filling up is taking a lot of space. So we're going to be filling up that space. We put this control valve in there. It starts up. The centrifugal pump needs to start against a closed valve. It will open as it sees system pressure. Then our bypass valve, if we're putting out more water than we want to go to the headers, we can preset this and it'll bypass back to the tank. So it's a little bit of a loss of efficiency if we have to do that, but we do have that capability. Some other quick comments about pumps. PD pumps have to be set on pads that have to have a concrete volume about 1.5 to 2 times greater than the pump itself. And I'll show you a picture in just a minute of how that pump needs to sit there too, because you can pour a lot of concrete and do no good with it. Pump metallurgy has to be selected to resist corrosive fluids. Aluminum bronze is commonly used with ceramic plungers. Those metals are some of the lesser cost that can be used. You can go all the way to stainless steel, or the extreme cases to stellite. But as we talk about those different materials, the cost go up. Most of our pump vibration and pulsation problems are due to poor suction conditions. That might be important enough for a quiz too. Most of our pulsation and pump fluctuations, the vibration, the pulsation, are due to poor suction conditions. We haven't satisfied NPSH, the pump stars, and the more we flood those valves, remember those valves that are opening 300 RPM and they're opening and closing and opening and closing. If there's not a water suction, a water flooded suction on that pump is going to beat those valves up. So most of our vibration problems are due to poor suction conditions. And generally we want to keep the suction velocity less than 1 foot per second on a high-speed PD pump. So again, here's our statement about capital costs plus operating costs should determine the type of pumps that are selected. Here's that drawing on pump bases. I don't expect you to be civil engineers on this design. Just understand that here's two triplex pumps, let's say. One's mounted on a base. The base is this thick. The other's got a nice thick base on it. But notice in this case, the triplex pump sits to the front of the base. And there's two forces that we have to take through the base. One is the back. There's always, for every action, there's an equal and opposite reaction. The reactive force coming back on the pump acts this way. The mass of the pump acts this way. Those two vectors intersect on a resultant. The resultant vector should pass through the entire base of the pump. In this case, they do, and we get a nice even distribution. And our pump, if it has any, it'll have a resistance to tilting back because of this vector passing through that base. In this case, we got a nice thick base, but the pump's mounted at the back of it. Here's our vector heading in the reactive force. Here's the mass. Those vectors intersect, but just through part of the base and don't go through the entire base. And so you could pour a lot of concrete, and this applies to compressors too. You can pour a lot of concrete, have it in the wrong place, and it doesn't do you any good. That's free. That's not on the test. Distribution lines coming from the pump. We go from the pump to distribution lines, and then from the lines to headers, and from the headers we go out to individual wells. Injection lines, buried steel lines need to be externally coated, especially in caliche. Caliche is especially corrosive to steel. Keep the lines out of the areas where there's old drilling pits, or maybe even old tank batteries, because the ground can be contaminated, makes that especially corrosive soil. Fiberglass reinforced pipe, or GRP, requires a sand pad when you bury it. You don't want to put that in a dig through rock and then put the fiberglass down and then backfill it with rock, and you'll chip it and break through it. So it has a sand pad below it and above it when we bury those lines. GRP pipe on the surface has to be painted to avoid UV deterioration of the pipe. The bonding material that holds the fiberglass resin will deteriorate with UV light. All the piping needs to be purged before startup. That ought to be a duh, you know. But as you weld pipe together, as there's pipe dough put in the lines, old rags, rattlesnakes, anything can get in those lines. I've actually seen a production header plugged with rattlesnakes before when it started up, because the pipe was left laying on the ground, and they made home there. So the piping needs to be purged. We go into all this trouble to filter and treat it and try to clean it up, and then if we pump junk through it on the first day out, we haven't done any good. We'll probably need to keep lines at 2 to 3 feet per second to keep them clean. Metering. Here's a number of places that we need to meter. We want to know how much we're discharging out of our station in total, how much volume we're putting at each header, how much volume we're putting in each well, how much water we're buying, how much produced water we're using, and any makeup water. Anytime we have a new volume come in there, we need to be able to have all of these volumes just to do a material balance, because we're paying for that water. One way or another, we're paying for it. And we need to understand where it's going. And as a production engineer, you'll need to be able to chase that down and understand where you have leaks or problems. As a reservoir engineer, you're going to want to know where all your water went. On metering, always place a strainer upstream of a meter, and most of the time now we're talking about turbine meters especially, because they're most commonly used in water flood operations. They're economic. We always place a strainer upstream of that meter. We shouldn't let the liquid go below the last separation pressure, because we'll tend to drop out gas. So if we have a meter coming, we have a water source, then a meter, then a control valve, we can hold pressure against that meter the same as that last pressure that it saw, then we won't spin the meter as a result of gas breaking out of those liquids. And then our bigger master meters need to have a bypass to allow the meter to be serviced. So at our header, we have a master meter hookup that would look something like this. Here's our strainer, here's our meter, and then valves to isolate on both sides. When we take this out, notice we've got a bypass loop that we can go around to get this to service it. The other things we'll see are sample points on a lot of our piping. You can't have too many sample points through your system to see what's going on in different phases or to measure pressures. At the injection manifold, now we're looking at a side view of what the stream would look like coming off the injection manifold. We go through an isolation valve. Here's our strainer, our meter, and our flow control valve going on out to the wellhead. And we'll look at each of these components separately. This is a multi-orifice valve that can be used as a choke on the water flood service. It has two discs in it. One of the discs rotates. And so full open, the holes in the disc align with each other. Then as we rotate one of the discs, we move the holes so that they're either fully open to it or partially open to it. And finally, we can rotate all the way closed so the discs are opposite each other, no flow can get to it. This makes a simple flow control valve for water flood injection. It's nice too because it handles some solids. It'll take some erosional wear and still make a good seal. So this looks different than the chokes you put on a wellhead. This is not the place for that, but this is a technology that can be used on the injection header. This is the strainer. Flow comes through it, goes through the element, and then back out and discharge line. Notice it's got a plug on it where that can be taken out and cleaned. We had a pumper once that he just finally took this out. We said, "Why'd you take it out?" He said, "I kept getting plugged up." And we're trying to save the meter, and he's just trying to save himself work. But if that ought to be a clue to you. You're putting something that's too dirty down that line if you keep plugging this up. But it doesn't need to be there to protect the meter. This is the turbine meter. Again, there's 2 or 3 manufacturers of this. I think you've seen this before from class on how it works. Turbine meter sizing. I've highlighted a 1-inch turbine meter. This is data on one manufacturer, but the rates are nearly the same for all of them. That 1-inch will do 170 to 1700. So it's got a 10-to-1 range on it. And that'll handle most of our applications. The other thing is that in practicality, you will seldom see anything this small, 7/8 to 3/8 inch meters in use in the oil field. Some dainty things just don't get worked right in the oil field. And some piping that's too small just won't take the abuse. So it has to be the right situation to use these smaller meters. But generally 1-inch piping is about as small as we'll see. There is a pressure drop associated with those meters, and the pressure drop on a meter is an indication of the health of the meter. So for that plot of pressure drop through there on our 1-inch meter, you can read for any pressure drop what the rate should be. And you're doing troubleshooting on your injection headers, if you see a high pressure developing, you know something's wrong with the meter. Or a very low pressure. It could be spun out, maybe the internal parts of it have gone on downstream somewhere. And so the pressure drop is a real clue as to the health of the meter or the condition of the meter. Finally, the wells and the well heads. Now, some of you are going to want to use an old producing well for an injection well. Fact of the matter, every water flood that has producing wells on it will use an old producing well for an injection well. What kind of problems might that make? Hasn't made any up to now. You guys have said in your design, yeah, we'll just convert these wells to injection and away we go. So what does that mean? What kind of problems could you run into? Leaks where? In the casing. Okay, the integrity's got to be good in the casing. What else? Okay, now hopefully we're going to put new tubing in there. We ought to take care of that. How about down on the perforations themselves? Would you do some cleanup there?
Yeah, work over.
Yeah, the old perfs, check TD, make sure they're not filled up, they're not over the perfs. There's a lot of things associated with that producing well that have gone on for years and years that now as part of your conversion process, you got to do a good thorough cleanup and a test of wellbore integrity before you convert that to an injection well. The wellhead hookup, here's another coming off the line from the header. Here's another sampling port, isolation valve, and then this is shown in Chevrolet. You can sometimes still find these unified injection heads that have a check valve, a master valve, and a lubricator point, all as one built-in unit. If not, you have three separate components of inserting a check valve, a master valve, and a lubricator tie-on point. The lubricator tie-on points are especially important because in injection wells, you'll find yourself running surveys. At the minimum, you're going to be going in there and checking TD to make sure you're not getting fill in that injection well. But you could be running spinner surveys or temperature surveys in the well to see what your injection looks like. So in the well itself, when we set the packer, we've got our producing perforations down here. EPA dictates to all the states, and the states adopted this regulation that that packer can be no higher than 100 feet above the topmost perforation. So the recommendation is to set it 50 to 100 feet. And why don't you want to set the packer right above the top perforation? Remember I said we're going to run survey tools through here, and one of them's a spinner. And the spinner survey works as we lower it down, it's going to measure the flow rates. And once we get out into open casing, we need a calibration area so that we have a point where we know there's no water injection. So we have this 100 feet between the packer and the top perforation for a calibration area for our spinner surveys. And then that way we can tell as we get in here, if we start seeing areas where it's taking water or it's not, and we can compare it to the 100% sure case where there's no water being taken. The packer, we need to make sure it's in the cemented interval, that this cement was brought above wherever we want that packer set. We've got to have an internal, either a lining on our tubing, or the tubing has to be made of a corrosion-resistant material. I don't know anybody that runs stainless steel tubing for water floods, but a lot of water floods do run tubing with liners. There have been cases in the past where a lot of people got the plastic lining. They didn't check though for gas permeability. You know, we're just pumping water. Well, water has gas in it, it's still being trained in it, and gas actually permeated the lining, got behind the lining between it and the pipe, and then when we shut the well in and there was no pressure in the tubing anymore, that gas popped the lining out of the tubing. So we also need to be concerned about the metallurgy in the packer. And it's either a corrosion-resistant material or it's a lined material in our packer. And then finally, we've got to keep cathodic protection on. Even though it's an injection well, doesn't mean that you still don't have that electrolysis action going on over the well. That is about all I had today. Do you have any questions? Okay, it's all yours.
You're not going anywhere yet. Okay. Oh, my shadow quiz. First down, give it to them. Don't take a look at it yet. Quiz will be last 5 minutes. So much, we have 8 questions and I think you can do all that. We will continue with multi-phase flow. I have already made the exam. The lecture that you have just now, it's not in the exam, that's why we give you a quiz. Multi-phase flow, I'm so sad, it's not in the exam either. Okay? And the next one, flow assurance on this coming Monday, is not in the exam either. So just pay attention with each part. Somehow test whether you know it or not, but this is just not in the exam. I will find some other way how to test you, okay? For the flow assurance part, this one is multi-phase flow. For multi-phase flow, every calculation that you are about to see will be about the real velocity. Okay, you need the real velocity. To get the real velocity, most of the time you don't have real velocity. Most of the time you have a standard condition gas, right? How many standard cubic foot, how many standard barrel. That's what you have. So from fluid property class, you have to be able to convert that into the in situ volumetric flow rate. For example, when you have some gas on the standard condition, you put that standard condition gas into the pipeline condition, it shrinks. It gets compressed, right? And some of the gas will dissolve into liquid phase, correct? So there's a phase change. So you use B sub G, B sub O, R sub S to account for all that. I don't teach you any of that anymore, okay? I assume that you know it. We will not cover everything on multi-phase flow. We will cover just, have you seen some of this for today? So, stratified flow, top and bottom flow separately. Elongated bubble flow, there's no air entrance inside, that's elongated bubble flow. We have slab flow, air entrance inside. And we have annular flow, gas in the middle, and liquid film on the top and bottom. Maybe I have just enough time to give you some introduction. If you have gas well, most time you have gas flow, not quite multi-phase flow. If you have oil well, you may have multi-phase flow. This for outward flow, you have this bubble flow, small bubble in the liquid phase, slab flow. I have seen that in the lab, churn flow, annular flow, and roasted. Before we go into our calculation, memorize one thing, okay? To simplify every calculation, what you can do is this. You assume that there is pressure drop when you go up, okay? Let's say you have up and down, two-phase flow, gas liquid flow. When you go up, you have pressure drop. When you go down, assume that you have no pressure gain. Okay? When you go down, typically if it is single phase, you have pressure gain, right? But if it is two phase, just a rule of thumb, just assume that you have no pressure gain. So that will give you some approximation. And if you don't consider any flow pattern, use pseudo single phase approach. Assume that gas and liquid are well mixed. Use the average fluid property to calculate pressure drop. That will give you estimation. Of course, when you mix gas with oil, viscosity go down. Okay? When you mix oil with water, viscosity go up. Okay? Viscosity go up. Water with viscosity of, let's say, 1 centipoint for water, 10 centipoint for oil. You put 1 centipoint into 10 centipoint. It doesn't make your total liquid to be like less than 10. Viscosity will be more than 10. Okay? Viscosity will go up. How much up? I think there's a formula to do that calculation. This oil water. And there are several flow patterns for oil water too. Flow pressure drop is flow pattern dependent. It depends on what kind of flow pattern we have. And there's a chart for you to read. VSL, VSG, VSL is superficial liquid velocity, VSG is superficial gas velocity. We will go back to that later. Let's take a look on this one, pseudo single phase. When I said viscosity go up. Why is my viscosity go up? When you have gas liquid. For today, look at this formula. Mu sub m. So this one for oil, water. Okay? If you add a little bit of water, like 0.5% into oil, viscosity can go down. But when you add like 1%, 3%, 5% of water in oil, viscosity go up. To calculate the mixture viscosity, do this, okay? Mixture viscosity is equal to continuous phase viscosity. Let's say oil is continuous phase. Multiplied by 1 minus HD, whole up of the dispersed phase. Let's say you have 10% water, 10% by volume. So whole up will be 0.1. Okay? 1 minus 0.1 is 0.9 to the power of minus 2.5. This gives you mixture viscosity. For density, for oil water, you do weighted average based on whole up. Whole up is a volume fraction. Okay, volume fraction. So whole up of water is a fraction of water in total liquid. So this is for oil and water. For air and for gas and oil, viscosity is just a weighted average with whole up. Okay, and density is same thing. Other fluid properties same thing. So this is for gas and oil. So this slide you have seen already is summary, and you by now you memorize that term already for the exam. Basically, I will skip all this, and my conclusion is this: mechanistic model is best. That's what you need to know. Just that. That there are empirical based model and mechanistic model. In short, mechanistic model is best. Okay, and you learn about that later. So one last minute before you do the quiz, let's take a look at the flow pattern map. This flow pattern map is dependent upon angle. VSL, superficial liquid velocity, is liquid flow rate divided by pipe area. Okay. VST is gas flow rate divided by pipe area. So depending on VST and VSL, it's not real velocity, okay? Depending on VST and VSL, then you can look what is the flow pattern. I is intermittent, SS stratified smooth, A is annular flow, DB is dispersible flow. We will continue the calculation later. So for now, write your name, okay, open it, and start doing it. I'll give you 5 minutes. So we will end at about 12, 20, 30. Okay?